Hello students, in your last engineering lab experiment internal forces, we demonstrated some basic concepts about equilibrium of structure and developed some principles for calculating the forces that develop within the members of structure when the structure is subjected to external loads. We also show you in the previous video tutorial about SAP 2000, which is one of the most structural analysis tools that is available uh, for civil engineer, also mechanical engineer, that how SAP 2000 can be used to calculate these forces in a in members of a structural systems. And you practice the software using simple trusses, 2D trusses, and you were able to extract the forces and what type of stresses and internal forces that develop inside these structures. In today's video, I will describe the primarily step-by-step procedure for designing and analyzing a Warren Truss bridge model. So it can help you with your projects, and it is recommended that you actually perform these steps using the program while you are watching this video. As I mentioned on the SAP 2000 introduction tutorial, the analysis procedure can be divided into three parts. So we have the pre-processing, the solving, and post-processing. The pre-processing step is where you define your unit, you define your geometry, material, you define your loads, cross sections. Then after that, it comes the solving part. This is where the software will solve for forces, stresses, and shows you the deformed shape of your structure. Then it comes the third step, which is the post-processing, and the main option in the post-processing will be displaying the deformed shape, displaying member forces, printing the results, designing the structure member, and checking for safety of the design. And also you can modify your structure. SAP 2000 is object-based, meaning that the models are created using members that represent physical reality. A member with multiple members framing into it is created as a single object, just as it exists in the real world. So the goal of your project is to perform the structural analysis of a steel truss bridge that spans a total distance of 63 feet, has a 26 and it's 26 feet wide, and the roadway is formed by one concrete deck with an 8-inch thickness. The truss bridge consists of two parallel trusses, and the truss configuration will be as shown in this slide. The lower chord of the trusses support the roadway, which in turns carry the cars and the traffic. So in this project, you will need to use SAP 2000 to design the bridge and calculate the internal forces in each member of the bridge under the effect of the weight of the bridge and the roadway, which we called the dead load, and the weight of the vehicles, which or external load that are likely to cross the bridge. In order to simplify the analysis process, it is assumed that the live load can be represented by track configuration shown in this figure, or as shown in this figure. The effects of this track is assumed to model the effects of the heaviest track that are expected to cross the bridge in its lifetime. At this stage, we assume that the steel truss members has a cross-section area of 20 inch square and are 836 structural steel members with a design safety factor of 1.5. The weight of each member will be assumed to be equally divided between two joints at each end of the member. Notice that every longitudinal position of the track will produce a different load distribution in each member. The bridge must then be checked for all possibility. Since the roadway is carried by the lower chords of the truss, then it is here assumed that the weight of the truck will be applied at the joints of the lower chord. We will assume that each axle of the truck will produce one load with a magnitude equal to the one shown on the picture, including the impact factor. To understand what is the impact factor, When the cars and trucks move across the bridge, they normally produce dynamic oscillations of the bridge structure. This dynamic oscillation will in turn produce force in each member that are higher than the force obtained if the load are statically applied. These additional dynamic force can be modeled using a dynamic amplification factor or what we call the impact factor. So in our case, we will assume that the impact factor is equal to 0.27 times the track load, which is a 27% extra load. This dynamic amplification load should be added to the load of the track. So the bridge also must be checked for all positions or all possible positions of the track, which will in turns produce a different load condition. So we will have different scenarios. So the first scenario or case one or condition one will be with just when the track just entered the bridge and applying load on the first joint, okay, supports of the bridge. Then we have the second condition as the track applying both the front and the middle wheel. Then we have three wheels. Then we have the whole track is in the middle of the bridge. Then as the track moving forward, each case will have a different load applied to it or different scenario. So let's start and modeling our bridge. So the first thing after you run SAP 2000, you gotta go to File to start a new model or begin a new model. Go to File, New Model, or you have this small icon. So go to File, New Model, right? Then you will see the first window, the New Model window. So the first thing you have to do is define your units. These are the default units that's going to be used by SAP on all whole modeling process. So to decide what unit we're going to use, if you go back to your problem here, so we have distances are in feet and forces are in pound. So we're going to select pound, feet, and the F here, the capital F, is for temperature. This is Fahrenheit, which means you can include temperature analysis in your or include temperature in your analysis, right? So then you have different templates. So the software SAP provide different templates. So you can either start from a grid, so a grid system where you can define your grid distances on the X and the Y and Z axis. And it's gonna also be used as a template for you to draw your structures, right? Or you can start from ready built and templates. For our case here, these are different templates based on the applications. In our case, we're going to use the 2D truss. So we're going to use the 2D truss and we'll convert this 2D truss to a 3D bridge, right? So click the 2D truss. So here the software will ask you about some information. So first you need to provide the number of divisions. So then based on our problem here, we have 1, 2, 3, 4. So we have 4 divisions. So we're gonna put 4 here, 4 divisions. Then the height of the bridge. So the height of the bridge is given as 1364 feet. So 1364 for the height of the bridge. Then we have the division length. So the length of the division is 1575 as shown here. So it's 1575. Then you click OK. So as you can see now, the software split two windows. We have two views. The first view is the 3D view, and the second view is the XZ plan view. So this is the XZ view. You can switch to other views from here. So you can see you can either go to set the views to your view to XY, XZ, YZ, or XY view, or you can put it as a 3D view as well. So let's go back to XZ view because this one shows us the 2D truss bridge. Now, as we said, we are trying to model a 3D bridge. Then we have to create a replicate of this 2D truss. So to do that, we select our 2D truss. So Control A to select all members, and you can see now are selected. You go to Edit, replicate. Okay, now we have to decide in which axis direction we have to replicate and what's the distance. Okay, at which distance we're gonna replicate. So the first, as you can see, these are the axes. So we want to replicate not on the z direction, not in the x direction. We want to replicate on the y direction. So it's gonna be on the dy, and the distance, as we know from the assumptions, the bridge is 26 feet wide. So our distance will be 26. And you don't need to specify the units as we already define our units, as you can see here on the lower right corner. So we have already feet here. So just put the 26 feet number. So now it gives you a replicate of the 2D truss. We just need to connect the lower chord and the upper chord. So to do that, on your left side, you have the toolbar. This is where you can select the tool that you're going to use to draw your frame or cables. So I'm going to select the draw frame cables. So you have this small window that pop up. So ignore it for now. So you can either connect your 2D trusses using the 3D view, or you can switch to 2D view. I will show you both options. Okay. So one more thing that I have to mention here, you have to make sure that the snap tool is active. These are the snaps, intersections tools. So when you have the snap tool active, as you can see here, when I highlight the corner, so when I move my cursor to the corner, you see a red circle that points to the joints. So this makes it easy for you to draw your cable without missing the joints, right? So let me draw the cables, the upper cables, using the 3D view. Then I will switch to 2D view and draw the lower cord cables, okay? So first click, let me make sure I'm selecting the draw. First click, second click, right click. So first click, second click, right click. Why I do the right click? Because if I just click and I keep clicking, you see it will follow me. I mean the cable will follow the motion or the movements of the cursor, and it will draw another cable on a position that I don't want to. So let's go back. That's why you have to first click, second click, right click means I finish with the point where I wanted to draw the cable. So now let's move to the lower chord. So I'm gonna do it in a different view. So you go to view, set to 2D view. So here I'm gonna put Z0. So I wanted to go to the XY plane and the Z0, which means the lower part of the bridge. So this is the lower part of the bridge. Same thing. You select the drawing tool, go first click, second click, right click, first click, second click, right click. As you can see it with the snap tool, you see it's easy to find out the joints. So first click, second click, right click, then first, second, right click, then the last cable or frame. Now I can go back to the 3D view. Okay, this is the bridge frame, right? Now I just draw the frame. As you can see, by default, I have the support added here. So I have one fixed support and one roller support. So I don't have to assign any support, right? The next step now is gonna be adding the material or defining the material. So there are two things. So first, you will need to define the material, then you assign it. As you can see here, the menus, we have define, okay, menu, then there is assign. So before you assign, you define your material. So first thing, we're gonna define a section property. So to our members, so we have to define a section. So we go to define section property, frame section, okay? So we don't have any section yet, okay? So I'm gonna go to import new property, okay? So the beams that we are using here are I-beams. I'm gonna select the wide I-beam, and we make sure that these are steel, okay, I-beams. So click I-beam here, and the software will ask you about the location of the file that define the sections. So select the last file here, which is section 8. So click and select it. So that's the section, and there is another window that will pop up. So first, let's define the material. So we said steel, but there are different standards of steel. There are different kind of materials. So we will have to define our material. We go to add new material, right? Steel, and the standard that we are using here is ESTM 836 steel. Okay, so select that one and click OK. And you can see it has been added here. So you click OK, right? And you make sure you select that material from your menu, from the list. Okay, now, as we mentioned at the beginning, we assume that the cross section here is 20-inch square. So, and from the list here, you can pick the cross-section area that you will use. You can pick multiple cross-section area, but for now, we're gonna start with the one that we assume will be used for our primarily model, which is the 20-inch square. So 20-inch square, it's W 1068. So these are, to understand these designations, so I will take you to this website, which is the that shows the steel sections classification or dimensions and property of majority of standard steel sections, American standard steel. So as you can see here, if we pick the W wide flange I-beam, okay, so it gives you this table, and from here you can see the W1068 has a cross-section area of 20-inch square. The other values or the other columns shows you the property of the depth, width, flange, and distances. So for now, we just know that W1068 is 20-inch square. So we go to our model and we try to find the W1068 here. So W1068 will be somewhere here. This is the one. So you click OK, and software will shows you the property of this cross sections. So these properties are the same one that you see here in these columns. Okay, so you click OK. Then now what we did, we just defined the cross section, right? So I'm click OK. Nothing happened yet because I need to assign it. So in order to assign this cross section, the 20-inch square, to all members, that's what we assumed. All members are 20-inch square cross section area. So I'm gonna Control A to select all members. Then I go to assign. So assign frame section. Then you can see now I can see my W1068. I'm gonna select that section and click OK. Now I have a 20-inch square cross-section area applied in all to all members, right? So we gotta do the same to define our concrete deck. So for the concrete deck, it's a rectangular, so area, okay, it's a rectangular shape. So again, we're gonna go to the set 2D view, XY, so it's applying the lower chord, XY plane, Z0. So this is the lower chord, and we're gonna select the draw rectangular area. So click rectangular. So click the first point and drag to the second corner. Okay, go to the select mode, select it. Now it's applied. There is one more step we have to do here, which is the mission or dividing the area. So we will divide the area. So you go to edit, area, edit, divide area. Okay, then here you have different options that you can use to divide your area. You can just divide area into these specific numbers, or you can choose divide area based on points or on area edges. For example, so I'm going to decide that I want to divide based on intersection of visible straight grid. Okay, so click OK. This is one option, and you can see here my area is divided to different small areas. So let's go to the 3D view. Okay, so you can display the area as a solid area. If you want to display this area as a solid area, you can select all area sections. Then you go to here, this small icon. Okay, set display. Then there is fill objects. So if you check the fill object, So it will show you the concrete deck as a red one solid area. Okay. Now we just defined the area, but we didn't define the material of the concrete. So same thing, we're gonna go to define, okay, section, okay, but this time is not, we're not gonna select frame section, we're gonna select area section, right? So same thing, add new section. I'm gonna call it concrete, right? This is the material we use for the concrete, so we don't have to change it. And for the thickness, we're gonna put the 8 inches. So we will put the 8 inches because it's divided to membrane and bending, and these are used to for in order for the software to calculate the moments. So only selects the membrane and put 8 inches, 8 inches, so 8 in, because as you remember, we define our units as feet, pound feet. If you put 8 only, the software or SAP will consider this value as 8 feet. So you have to decide that this is 8 inches, and if you click outside, the software will convert this value directly to inches, which is 0.666. So we click OK, right? So I define my concrete property material. Now I have to go to assign. So assign frame area, okay, so area section. So assign area section. Then you select your concrete. Then you click OK. So we have the property material changed again for the concrete. So there is one more step that we have to do here, which is we have to release the moments, okay? So this is a very important step. So you go to, first you select the concrete deck. So you go to assign area, okay? And area stiffness modifier, right? Then here, from here, you can modify your membrane, okay? So we're gonna put 0 in the F11 and 0 in the F22. So we modify our factors, okay, membrane factors. So now we're done. We define our geometry, cross section, material for both the concrete and the steel members. Now the next step we in our pre-processing is to define the live load. So whatever we did now, the software will use it to calculate the dead load, the weight of the bridge, and this is going to be used to solve for the forces. But we need to add the external load, which is the load of the truck. Now let's go and add the live load. So we said the live load is the external load, which is due to the vehicles that will cross the bridge. In this case is the track. So as we mentioned before, we add a impact factor. We use an impact factor to add the extra dynamic load or dynamic oscillations. And these are the load that we found. So after adding the extra load, the 27%, so the front wheel will apply 10,160. The middle and the back wheel will apply 4,640 pounds. And as we mentioned, we have different scenarios that we have to consider and that the software will use to solve for the forces. So we call them cases or loading condition. So we have case 1, 2, 3, 4, 5, 6, and 7, right? So let's go and add case 1. So case 1, as you can see here, it's when the track just entered the bridge. So we have the front wheel applying load here on the first joints. So I'm gonna go, I will select, sorry, just click to select, see how they are selected. The first joints have to go to join load forces. So I already defined my load here. In your case, you will find only the dead load. So how I define it, I just add them from here. So just define the load condition. So you choose what type of load, then you click add and you will add it. So that's how I add all these cases from 1 to 7, right? So I'm going to select case 1. And as we mentioned, case 1, the first value will be applied on the Z direction. Why Z direction? As you can see, these are the axes. coordinate system. So X, Y, and Z, and the load is applying, uh, it's going to be perpendicular to the concrete deck. So it's going to be a gravity load. So it's a Z, but it's a minus because it's going down. It's the load is applying a gravity as a gravity load. So that's why we add the minus value here. So the value is 10,160. Where we got this value again? We got it from our calculation. Okay, so you click OK. So this is case one, press OK. As you can see, SAP will show you an arrow with the value, so the arrow pointing down. If you miss putting the minus value, you will see an arrow pointing up, which is wrong. So this is a gravity load. So let's go to the next loading condition, which is case two. So we have the front and the middle wheel. Okay, so the front wheel will move forward. So we're gonna move the 10,160 one step forward. So you have to select case two and press OK because the value is still there. Then for the same case, you're gonna go and assign join load forces case two, but the value here will be 4640. Okay, so front and middle wheel now apply. So now let's go to case three. So case three, which is this one, we have all the wheels in the bridge, apply load on the bridge. So we're gonna have the front wheel will move here. Okay, so assign join forces. So now we know the value is 1,160. It's okay. Oh, I made a mistake here. So that's why I have to make sure I select the right case. So I'm gonna go forces, make sure you select case three. Otherwise you're gonna apply to the case two. So it's case three will be here. Then again for case three, select all the four back joints, the middle and the back. Then you click forces, case three, but the value here is 4640. Okay. It's case four, same thing. Front wheel moving forward. Assign, join forces. Okay, it's gonna be case four. It's 10,160. Then again, the middle and the back wheel applying load in these joints. Load is 4640. Now that we add all the loads, we still can go back and check if we add them properly. So to do that, you go to display, show load, assigns, join, right? And it will ask you what load pattern you want to see. So you select the load. Let's select case one. Click OK. As you can see, it's showing case one, and we have the 10,160 pound applied to the first joint. So to see the other cases, you can just use these arrows here, and you can move forward or backward, simulating the track. So moving forward, we see that the 10,000 move one step, and we have the middle wheels moving to the back joints. All right. So case three, and as from here on the third tab, you can see that the cases are changing as well. So case four, this is where the track is, the whole track is applying the load. So the track is in the middle. It's a critical load. Okay. Case five, case six, seven, and track left the bridge. Right. Now that we have assigned the loads, we're done with the pre-processing step. So now it's SAP 2000 turn to solve the forces for us based on all this information. So that's why you're gonna make sure that you provide the software with the proper units, the proper information, the dimensions, and all the material needed. So to run the analysis, we're gonna go to analyze, run the analysis, or you press F5. Another way to do it, you just click this small icon here, the play icon, so run analysis, okay? Then you click run now. I think because I run the model before run the analysis, it's not going to ask me to save, but for you, in your case, the first time you run it, it's going to ask you to save the model, right? And make sure you save it in a folder, because SAP 2000, when it run the analysis, it will create a bunch of folders. So you want to make sure that you have them all in the same folder, right? Okay, so these are the files, for example. Then when the raw software runs the analysis, the main file that you have to save and you make sure you don't remove is this one, which is the SDB file. So this is the model, and this is the one you can share with other students or other members from your group to work on, okay, or collaborate on. So this file is the main file. The other file will be created if you when you open again this file using SAP 2000, then run the analysis. So make sure this is the file that you don't remove, right? So let's go back to SAP. So now I'm gonna click run now. So it said no cases to run because I ran it before. So when you run the model, the SAP 2000 will lock the model. So you cannot modify it, you cannot change it. So you have to unlock it first if you want to make any changes on your members sections or in your forces, live forces or cases, right? So let's run it again. Run. And I forgot to mention, when you run the model, we have to keep the dead load. Okay, we have to include this in our analysis. The only one that do not run is the modal. Okay, this is for dynamic analysis. So keep the dead load on the other cases. So run again. Okay, it's running. Okay, so it finished running. It shows me joins reaction. So I wanna let the software to display other information that I might need. So in order to see, for example, the forces, I'm going to go to display, show, oh, before the forces, we can see the deform shape. So let's click deform shape, and there one of the conditions, let's say case one. So here nothing happened, okay, because the track still applying load on the first joint where we have a reaction force. So it's reaction supports, the supports. So, but if I move forward, case two, you see the bridge starts bending, and the software shows the exaggerated bending of the bridge. So this is a exaggerated deform shape. In real life, we have the bridges also bend, but we cannot see them as they are in macro scale. So let's go to the case 4, case 5, and the bridge still bending until case 7, which is like case 1, right? What other information we can extract? We can check the forces. I'm going to show forces, show stress forces or forces stresses, frame cables, F8s. Then you select which case you want it to run or you want it to display the force. So make sure you select the force. You can also choose stresses if you want to check the stresses in each member. And you have different components of the forces. In our case, for this project, we're gonna, this is where you learn, most of the forces are here. The one you learn on previous experiments is axial forces, so either tension or compression. Okay, we learn also about the moments, but in this case, for this project, we're gonna focus on axial force. Okay, so select axial force, scale and keep it automatic. And here in the options, you have two options actually. You have either the fill diagram or show values, right? So let's select fill diagram. Okay, so nothing happened because this is case 1, right? So the truck's still not affecting the member of the bridge because we have a reaction force applied by the supports. But if I move forward, okay, case 2, we have forces that develop in each member, and the magnitude force, as you can see here, changes from one member to another. And this color coded figure, the colors here give us information about which member is under tension and which one is under compression. So blue is under tension and red is under compression. If you move your cursor on each member, you can see the force under that condition. So for example, in case 2, we have this member will have an internal force of 8,634 pounds, right? As you can see from another member, you have different force and so on. Now let's move to another case. You can see case 3, case 4. This is where the truck is in the middle. The force changes, so we have 75. So as you can see, the magnitude, this rectangle shows you the magnitude of the force. So short, small rectangle, less force, and big rectangle shows higher force. Okay, so the maximum force is applied in this member, which is 75,000, right? Second, you can see these are compression forces. Also, they are minus, as you can see here, compression forces, and these are tension. Let's move. Case 5, case 6, and case 7, same as case 1. Okay, if you want to display directly the numbers or the values, you're going to go display, show forces, stresses, show for cable, show frames, cable tendons, or F8. You have also another quick access to that option. You go here, show forces, frame and cables. This time I'm going to select show values on the diagram. So here it shows you the values of the forces, internal force, under that proper condition. Okay. So something I have to mention here, when you run the analysis, as you can see, it shows you the forces in different conditions, different cases. Okay. So the forces here are only for in the case 6 or the loading condition 6, right? So it does not include the dead load. Okay. So this is not a combination of force. So, but SAP automatically creates a combination of forces. So one of them here, as you can see, so these are the combinations. So these are the cases that we create. This is the dead load, and these are the combinations. So we have DSTL1, DSTL2, 3, 4. What these combinations mean, these are, like for example, DSTL4, and this is the one you're going to use to optimize your bridge, to redesign it. DSTL4 is a combination of all cases plus the dead load. How to verify this? You're going to go here, define. You can define your own combination actually. So you go to load condition. So DSTL4, okay. If you click modify, you can see DSTL4 is all cases plus the dead load, right? Okay, that's the DSTL4. So it's a dead plus live deflection. So it's a sum up of the dead plus live. Do you want to add? You can add your own combination. You call it my combination or something like that. Then you select what cases you want to include in your analysis. For example, let's say we want to select only case 4, which is where the track is in the middle. Okay, then I'm gonna add it, and I add also dead load. Okay, the dead load, and I have my own combination that I can use in my analysis. In our case, you can just pick the case 4. Let's go and check DSCL4 or the combination. As you can see, you might say that case 4 is where we have the maximum force. If we check case 4, we have only 70, we have 75,000, 176,000 pounds, okay? This is not including the dead load. Now, if we can include the dead load and other cases, which is the DSCL4, you're gonna see that the force here is, the internal force in this member, sorry, is 269,000. So the maximum force is under that condition. And this is the one, guys, you're gonna use to solve your project, your problem, okay? To optimize your bridge, okay? So DSCL4. In some cases, when you run, you might not find these cases. Okay, I mean this DSCL 1, 2, 3, 4. You can add them as I show you, or define them in your define option or define menu. You can add the combination of dead plus live load, right? One more thing we can extract from the software, the model, is is this one, which is called Start Seal Design. So you go to Start Seal Design, you check your design if it's safe or not safe. So you click this eye directly, and the program will shows you a color-coded diagram. Okay, so this color-coded diagram shows ratios. So these are ratios of dead to the live plus dead load. Okay, when the ratio is more than 1, you will see red members like this. So these are overstress. When the ratio is between 0 and 0.5, you will see blue colors, something like this. These are over design. So your goal, guys, you have to change the cross sections. As you can see here, I just changed this cross section to show you the red color or the overstress. But in your case, because we assign the same cross section to all members as the first stage in our analysis, you're going to see W1068 as well here. Okay, so we want to optimize these guys that are blue, which are over designed. So we want to optimize and keep in also making sure that the member is safe. Okay, so in total or in general, we want to make sure that the bridge is safe and trying to optimize the costs, because when you lower the cross section, you are lowering the costs. Okay, so your goal is to change these colors, okay, and get a maximum of green colors, which are ratios between 0.5 and 0.7. So how to do that? Using all the information that the software will provide you, the forces and stresses. You can also check the tutorial and the manual that we provide you, and also the websites where we explain how to calculate the area or the optimized area. So you have to consider the safety factor, which we said is 1.5, and from there you calculate the allowable stress, and using the stress is force over area formula. So you have the force that you can get from the software. You substitute the stress with the allowable stress, and this is what we did here. And from there, you can find the minimum cross-section area. So that's the minimum cross-section area. And we don't want to use the minimum. That's why you have to create an Excel file, which shows like 5 columns, 4 columns. So the first column is the member number. The second one is the combination force, or the force combination, which is DSCL4, the one we use. Then you have the minimum cross-section area. So the required area is the minimum plus a margin value, plus a value here. You don't want to use the minimum, okay? So from there, one thing I wanted to add is to display the member numbers. If you go back to the software, let's change it to 3D. Okay, you go to set display, and you have labels. If you click labels here, you can see the members. So go to the XZ plan again. So 1, 2, 3, 4. Then you have 5, the other direction, the other side. Okay, then you have a total of 39 or 40 members. Okay, so these are the member numbers. Then you have the DSCL4. I show you how to get the force in each member. So you gotta go and check the force in each of the members. Then from there you calculate using Excel. Manually, you can automatically you can calculate the minimum cross section area, and add another formula to calculate the area required. Okay, and that's all for now. Thank you.